Good afternoon, one and all present here. I am Monalisa from Clarinet, the designated session assistant for this seamless interaction. Clarinet is India's most trusted and widely used digitech platform, offers a wide array of enriching services exclusively for doctors. We are very much delighted to be a part as a digital partner for this event organized by All India Institute of Medical Sciences partner. And today's session is all about Cox proportional hazard model. So thank you for your patient listening, everyone. So let us get started with today's session, for which I would like to invite Dr. Pragya ma'am to take the session forward. Over to you, ma'am.
Thank you, Mona Lisa, and thank you, Team Clarinet. So we'll start with this today's session. Let me share the screen. So good afternoon to everyone. And this is the continuation of the previous session which we took as a survival analysis. That was the basic of survival analysis. And today, in the last session, we covered some basics of survival analysis, the life table method, and Kaplan-Meier survival analysis way to see the cumulative probability of survival. In today's session, we'll touch a little bit upon the Kaplan-Meier, and then we'll again go towards the Cox proportional, because for those of you who are new to this session, it may be just a revision for all of you. And I'll be telling a little bit basics of JAMOVI also, because participants, the lot of participants, they are new in every session. So I'll be telling a brief description of JAMOVI also. So as we all know that this time to event data, this is a special type of data, and for which there along with the outcome, because in linear regression and in logistic regression, and in the entire session, I'll be comparing this Cox proportional hazard with the logistic regression and the linear regression, because all these three are a type of modeling technique where we model the data, where we predict something. Whereas in linear and logistic regression, we focus more on the outcome, where we see only outcome is okay. Dr. Poonam is writing that it is not. I'm not audible clearly. Okay, Dr. Gupta is writing that voice is fine. Okay, thank you, Dr. Gupta. So we can see that in logistic and linear regression, we are focused only on the outcome, where the outcome, whether it has happened or not happened. Whereas in survival analysis, there are two dependent variables. And in the last session also, we discussed a lot about this, that the dependent variable, the first variable is whether the event has happened or not. And the second variable, okay, let me check with the audio setting once again. I'm sorry. So this is the, I did it before also.
Okay, nice.
Okay. So I hope it is better. Dr. Rakesh, Dr. Vikas, is it okay now? Okay, thank you so much. So I was talking that in the case of this Cox proportional hazard, or in case of time to event data, there are two dependent variables. First is the whether the event has happened or not happened, like we see in case of a logistic regression. And the second, we see the how much time it took to happen that event. So that's why we say that we are having two dependent variable here. And that's why this survival analysis is little different from the logistic and the linear regression. So in this entire 90-minute session, we will talk with reference to this article. This article we have taken, the title of this article is Breastfeeding Education, Early to Early Skin Contact, and Other Determinants of Exclusively Breastfed Babies in Urban Population, which is a prospective cohort study. And in this study, they have used survival analysis as a main method of analysis. We have shared this article to you people, and we have shared the data set also with all of you. So those of you who have joined us earlier also, who have JAMOVI in their PC, you can simultaneously, you can also do the data analysis when I'll be performing the commands, so that you can learn it in this session only. And all of you can open this article also, and you can see like overall table of this article. Generally what they have taken, like they have followed up the dyad. Dyad is what? A pair of mother and the baby. And the event which they have defined, it is the termination of breastfeeding for 180 days, because 180 days is the 6 months. So they have followed the dyad for 6 months, and then they have seen like whether what were the factors associated with the termination of the breastfeeding. So we are sharing. Lavanya has requested to share the data set again. Okay, let me see. No. Am I still audible? This na Lakshmi network is better. Okay, so sorry for that interruption. I'll again share my screen. Yeah, so we'll share the data set once again with all of you so that you can work simultaneously. And we are sharing this article also with you people. So now talking about this study, so they have used the adjusted survival and unadjusted survival. So what is a adjusted survival basically? So this first we'll talk about unadjusted. So like I said that I'll always be talking in context of the logistic regression, because I assume that all of you know how to perform a logistic regression, that binomial logistic, and how to interpret that, because it is very much similar to the logistic regression, binomial logistic regression. So in binomial also, you know, there is something known as the unadjusted odds, and there is something known as the adjusted odds. In survival analysis also, you will see that there is something known as the unadjusted survival curve, where you take only one variable and you see the survival time across those two variables, that variable, like category of that variable. As for example, in this survival curve, you can see that in this case, my independent variable is the marital status, which has been classified as single mothers, mothers who are not married, and mothers who are not single. That I have classified it as other. And the article also has classified it as other. So this is the unadjusted survival curve for marital status of mother for termination of exclusive breastfeeding. And if you see here, it is the output of JAMOVI, and we'll see. So this is the unadjusted hazard is 1.45 with a confidence interval of 1.07 to 1.97 with a significant p-value. And what does it show? It shows that you can see here this orange line and the green line. So the green line is for others and this orange line is for the single. So the survival is more, that means survival probability is more with this green line, which are not the single mother. And the mother who were single, the survival probability is less. That means the curve is dropping fastly as compared to the other group. But this we are studying unadjusted survival, like unadjusted odds. And here we are only taking the marital status of the mother as one of the factor. If you take the unadjusted survival curve for education level of mother, so there is some echo somewhere. So the unadjusted survival curve for education level of mother for termination of exclusive breastfeeding. So again, you can see here that levels are divided into the higher and the lower levels, and the hazard ratio, which is a univariable hazard ratio. Why we call it as a univariable? Because there is only one independent variable. And many times you will see that people, they use term variate, univariate and multivariate. But that term, if you see many articles, they say that variate term should not be used. It should be variable. So if you are talking about the independent variable, it should always be variable, not the variate. Variate term which we use, that is in context of the dependent variable. So that's why in this case, I will see that it is a univariable because there is only a single variable, which is the education. And if you see the survival curve, you can see that this blue line is for the higher education status and this yellow line is for the lower education status. So survival probabilities are more for women who are belonging to lower educational group as compared to this higher education. And in this case, you can see a blank here. Blank means it is taking higher as a reference. So it is saying it is 0.63. We'll see the interpretation also. But if it is less than 1, then we can say that it is protective. That means a lady belonging to lower education, having lower educational status, is protective for termination of exclusive breastfeeding. So that's why you will see that Kaplan-Meier curve here, it provides a visual representation of the survival probability over each level of education, showing that the mother with the higher level of education had poor survival rates. So in this case, this was regarding the univariable survival analysis or univariable hazards ratio. So, but can we think like that mother who is having a higher educational status are like more, there are chances more that they will not be married? That means single women will be more, if we assume that can there be one possibility that in higher educational status, there are more women who are single. And that's why the effect which we are getting for a single status, it may be due to the higher educational status of the mother, not due to the single marital status. So this is the limitation of the Kaplan-Meier analysis. Why? Because in Kaplan-Meier, you can see the survival probability only across one variable. If there are many variables, you cannot see the survival probability because it does not account for the impact of other variables. And we know that in life, we don't have only single thing which is going on. There is a lot of interplay between these variables. That's why initially all survival data, we do the Kaplan-Meier. But again, if you want to model your data set, then the Cox proportional hazard is really needed. So it does not account for the impact of the other variable, that Kaplan-Meier, which might influence our outcome, which is the termination of exclusive breastfeeding at 180 days. So the other survival factors can be like gender of the baby, it can be educational status of the mother, it can be like skin-to-skin contact. Mother who are giving more skin-to-skin contact are having more survival. That means the termination of exclusive breastfeeding is not in less than 180 days. And the breastfeeding within 1 hour, that means the early initiation of breastfeeding. So these are the other factors where the event, that is the termination of exclusive breastfeeding at 180 days, that is dependent on all these factors also. And that's why we need to study this along with taking the other factors into account. And this is where there is a role of the Cox proportional hazard model. So this Cox model that allows us to include all those additional variables or the covariate in our analysis. And by doing so, again, we can understand how the effect of marital status is getting influenced by the presence of other factors. So this is the adjusted survival curve. In the beginning, what we saw, that was the unadjusted. Unadjusted means we are taking only one factor. Here, it is a unadjusted survival curve for marital status for the termination of exclusively breastfeeding. And what are the factors for which I have adjusted this? So I have adjusted this for the gender of the baby. You can see in the bottom, I have written here that this is adjusted for the gender of the baby, education status of the mother, skin to skin contact, breastfeeding within 1 hour, number of breastfeeding education session taken. So that breastfeeding education session is during the antenatal period. If you go through this article, there one of the intervention was, again, it was not an intervention, means they have also tried to give the number of breastfeeding education in the prenatal period or the early antenatal period. So that also they have taken, and I have plotted this curve adjusting for all these factors. So even if you adjust for all these factors, you can see here that the survival probability is less for here single mother, and it is more for mother who are not single. That means who are married. So this is the adjusted survival curve. So adjustment in this context, what does it mean? So adjustment means that we are trying to control for the confounders, because initially we have seen that there is an interplay between all the variables, and we don't know whether the other variables are acting as a confounder for this variable effect or not. That's why the adjusted hazard ratio, it removes the possibility of the confounding effect, because it gives you the value after controlling for the other variable, which we have seen just now. So after adjustment, we might find that the initial, what we observed initially, that the mother with a single marital status, they were exclusively breastfed for shorter period. But that same result was still valid even after controlling for the other factors like education, baby's gender, and the other factor. So that we can say that the marital status is an independent predictor of the exclusive breastfeeding, because its effect, it did not get changed even if we took another variable or the all other variable into the account. And we can say that now we can say that the relationship between the marital status and the breastfeeding duration, it changed after adjustment, and this indicated that there is an observed difference in the breastfeeding duration by marital status, because it is actually whether it was due to the difference in this marital status or other factors like what we have seen, like education, skin to skin contact, or the number of breastfeeding session. So if there is a relationship change after adjustment for additional variable, it is known as the confounder. And what is a confounder or a confounding? So confounding effect or confounder, it is identified or it happens when the effect of the primary variable of interest, which is the gender was in this case, is mixed with the effect of the other variable, and that is also associated with the outcome. So this adjusted model, or we can say that the Cox proportional hazard model, is a one way where you can control for these confounders and you can see the independent effect of the variable over the outcome, taking the time to event data. So Cox proportional hazard model, it adjusts for the confounding by including the confounding variable as covariate in the model. Now, how does it estimates the adjusted hazard ratio? So basically, what do we mean by this adjusted hazard ratio? So we say that the effect of the primary variable on the outcome, it is same across all level. That means it calculates the effect of primary exposure as if all study subjects were the same with respect to the confounding variable. Now, as you see that there is a name suggest it is the Cox proportional hazard model. So now there is something known as the proportional hazard assumption. So we'll be touching briefly upon this proportional hazard assumption. So one key assumption of this Cox model is that the effect of covariate. What is a covariate? All the independent variable in the model are known as the covariate. So effect of those covariate are multiplicative. And we'll see that it is constant over time. That means if you follow the hazard curve over time, the gap between the two curves is same and it does not change over the study period. We'll see how to plot that and how to interpret that. So let's understand this with a simple mathematical calculation. What do we understand by this proportional hazard assumption? So in this picture, you can see that this is a male and this is a female. So in the start time, if you see that here, it is the 0, the value, any outcome variable, let's say you are taking it as this is 0 and this is 2. So at 3 months, if I want to maintain the same difference between male and female, then what value should I write here in this section? Different. So 3. Yes. Dr. Rath is writing 0.5. But if you write 0.5, then the difference will be 1. Isn't it, Dr. Rath? If you write 3.5, then it will be 2. Yes, agree. So it will be 3.5. What about at 6 months? If I want to maintain the same difference between male and female, what should be the value? All of you please type in the chat box. It should be 5.5. Then it will be 2. If you are writing, yes, agree. So it will be 5.5. What about at 9 months? So 9 months will be 5.8, agree, and it will be 6.4. So this is across the two group if you want to maintain the same difference between any two outcome, which you can see here at different time point. That means start time, 3 months, 6 months, 9 months, and 12 months. Then coming to next, this thing, here you can say the question is changed here. Now I want to maintain the same ratio between a male and a female. Can you do it now? At 3 months, what value should I write here? Here, instead of difference, I've written ratio. So it is 3, agree. In case of 3.5, it will be 7, agree. And in case of 3.8, it will be 7.6, yes. But it is 7.4. Here, what I have written. And it is 8.8. So we can say that nearly it is same across at 9 months. There is a slight difference, like instead of 7.6, it is 7.4. But can I say that the ratio between the male and female are constant across each time point? So now consider a hypothetical study where I want to see the effect of gender, whether on the second attack of MI. So my study subjects will be all those people who had a first attack of myocardial infarction, and I want to see like in what time they will have another second attack of myocardial infarction. And I want to see whether it will be early in male or early in female. So this is the hazard ratio. I've not told you hazard ratio till this time, but just think that this is same like odds ratio. And here you can see that at the start it is 1 and here it is 1.2. At 3 months, the hazard in female is 2.2 and hazard. And what is my event? If you can recall the last session, we have defined what do we understand by survival time, what is the event, how do we define event. So in this case, what is the event? So event is the second attack of myocardial infarction. So that this is at 3 months, it is 2.2. And at this hazard ratio at this 3 month is 2.6. So what is the ratio? If you can divide 2.6 divided by 2.2, what will be the value? All of you, please do it on your phone, or you can do it roughly. Yes. 1.3. 1.313 is to 1. Okay. And what about this? 3.7 and 3.1? What is the ratio? 1.18. Okay. So you can see that hazard is changing with time. In this case, you can see that the hazard is changing. Yes. And here you can see in male also the hazard is changing. But if you see the ratio of these two, the hazard ratio is same, nearly same across these two categories in the different time point. So in the previous example, we can say that the effect of gender on second attack of heart rate is same across each time. Why I can say that? Because even if the time where there are various time point, but I can say that the ratio is same. That mean I can say that the effect of gender on second heart attack is same across each time point. Now, if you see this, then you will have to comment again. In the previous case, you have seen like some pattern like this, where the hazard ratio in both the categories changing, keeping the same ratio. Now consider this new result in comparison to this previous one. What can you see here? That in the start, it is like 1 and 1.2. Now, what is happening here at 3 months? So at 3 months, you can see that it is 2.5 in the male and 2.2 is in the female. So can you take out the ratio of 2.5 divided by 2.2? Yes, let me see the chat box. So it is 1.19 after Nikhil, I cannot see. Yes, Lavanya is writing 1.13. What about this? If I ask you to point out at this level, this one. What is the ratio of these two? 3.9 by 3.5. Again, you can see that it is nearly same. If you write like 5.5, 1.1, Rakesh is writing, Lavanya is again writing 1. So it is not exactly 1, it is more than 1. And if you see, it is nearly 1.12 or 1.2. So we can say now that the effect of gender on second heart attack is nearly same. So what the term which I have used here, it is not exactly same, but it is nearly same. Why I am saying it is nearly same? Because I can say that it is rough. Exactly, it is not 1.2, but it is very much near to that 1.2. Yes, you are right. So just a sec. So now see this, the next one. In this case, you can see, compare it with the previous one. So now see the ratio. It is 1.2. If you see this 3.4 and 2.2, then again 1.8 and 3.1. This is 0.9 and 3.5. and this is 8.2 and 4.6. So what is your interpretation now? Yes. Can you say that the hazard ratio is same? No. Dr. Rath is writing decreasing. Yes, so it is not the same. At each time point, the hazard ratio is different. So you can say that this is not like going with the proportional hazard assumption. So with all these examples, what I want to say, that the proportional hazard assumption holds true if at each time point the hazards are different, but the ratio is same. So now what can we say? So we can say that the effect of gender on second attack of MI is nearly same across all time point. Can I say that? Yes, yes and no. So there are mixed responses. So yes, we cannot say now because the hazard is neither the hazard is same nor the ratio is same. So we cannot say that. So we will say that the gender has a different effect on second attack of MI across various time points. So do you agree with this? Yes. We can say that it has got different effect on each time point, like 0 month, 3 months, 6 months, and so on. So once again, coming to the survival analysis. Why do we do survival analysis? Because the rates are not constant. And that's why there is a term which is known as the instantaneous hazard. In survival analysis, because you know that whenever a person have a first attack of myocardial infarction, the risk of or the rate of the second attack of MI will not be same during the entire period. Rates are changing. Even after surgery, you see that the risk is more during first 7 days, and then the risk starts decreasing. That's why the other value or the other measure, like the incidence density, that is not a suitable measure for this time to event data, because we see that the rate is changing. So rates are not constant even for a shorter period of time. And that's why in if you see the mathematical, because we are not telling you all those mathematical background of this survival analysis, because it is difficult for medicos like us to understand those difficult mathematical jargon where they have used the calculus and other mathematical formulas to define this. So just to understand, this hazard rate, or the hazard is a instantaneous risk of the event, and this rate is not constant. This is changing every time. As you can see that the risk is of death is very high immediately after the heart surgery, but it falls when the patient recovers, and then it rises again. Similarly, the recurrence of tumor following any diagnosis and treatment, initially it is less because right now the surgery and you have given the chemotherapy. But as the time passes by, you will see that the risk again starts increasing. So we say that this hazard, which hazard function. So there are two terms, and in the last session also we have talked about these two terms, which is the hazard function, and there is another function which is known as the survival function. So this hazard function is HT, which is the instantaneous rate at time t, which keeps on changing. Now, why this Cox proportional hazard? Because you want to take a reference. So you assume that the hazard in time t in one group. So this H1T is the hazard in the exposed group at time t, and this H0 is the hazard in the unexposed group at time t. Because what you say, you want to compare the ratio across two groups. So that's why you will say that H1T, in the denominator, you will take the H0T, which is in the unexposed group. It is always constant. And this assumption is known as the proportional hazard assumption. Like we have seen in the previous example, the hazard was changing, but the ratio was constant. So this ratio of H1T by H0T is zero, always constant. And this is known as the assumption of the proportional hazard. And this is again, we call it as a Nelson-Allen estimate of the cumulative hazard function. And it says that if the proportional hazard assumption is correct, then the graph of log of cumulative hazard function in the unexposed and exposed group will be parallel. So now this is the interface of the SPSS, and today we'll tell you a few functions on SPSS also of checking this assumption. So this is the Kaplan-Meier interface in the SPSS. And again, like we have said earlier, here you will see that you can have only one factor here as a comparative factor. And that's why to control for the confounding factors, you need the Cox proportional hazard model. So in the Kaplan-Meier estimate, what do? We see that whether there is a difference between the survival probability in the two group or not. And if there is a difference, is it statistically significant or not? And we have seen that we used various tests. The most commonly is the log rank test. There are others are like Taron-Ware, then the Pito-Pito. That option is there in the JAMOVI. So these are the tests which we use to compare the survival probability across two groups. But log rank is the most commonly done to check for the statistical significance. But like I said, that it also does not take more than one factor into account. So here you can see that this Cox proportional hazard model, this is again very much similar to the logistic regression. And the result of logistic regression is expressed as odds ratio, whereas the results of Cox proportional regression method is expressed as the hazard ratio. Now, there are few assumptions to check. So basically, we check two assumptions in case of this Cox proportional hazard. The first assumption is the, like as the name suggests, assumption of proportional hazard. And this we check with the log minus log curve. I'll show you how to check. And the second is the multiple collinearity or the multi-collinearity between independent variable. And this either you can check by the standard error value or you can check by plotting a scatter plot. That means seeing the correlation matrix. If the value of correlation coefficient is like 0.7 and more than that, then you say that it is highly correlated with each other. And this is done only when you have got more than one independent variable, which is continuous in nature. Am I making myself clear or not? This multiple collinearity testing is done only when you have got more than one variable which is continuous in nature as a independent variable. We'll see that. Like in this case, the dependent variable was the termination of exclusive breastfeeding with time. And the independent variable, if you take the birth weight of the baby as well as the gestation age. So these two variables both are continuous or the scale variable. So there are high chances that these will be correlated with each other. So if there is a high correlation, then you should not take both the variable. Why? Because then you will not be able to say that which variable is influencing this termination of breastfeeding. And that's why you should take out of these two only one variable. So that we check by the multiple collinearity, that is by applying correlation. And that is there in the JAMOVI. We'll see how to do that. So this proportional hazard assumption, this says that the relative hazard over time are proportional. And how to interpret this? It says that if the risk for dying at a particular time point in one group is twice that of the other group, then at any other time point also, it will still be twice than that of the other group. That means this hazard ratio does not depend on time. Now, what is a hazard rate? So in the last class, we have seen regarding the cumulative probability. And that Kaplan-Meier is a method of estimation of this cumulative probability. Because we see that over the time, and that cumulative probability is what? That is a conditional probability. You can see the earlier session where we have defined that the probability of surviving, like if we are following few people for 5 years, then how do we calculate that? We first calculate what is the probability of surviving for first year, then we calculate probability of surviving till second year for all of those people who have survived till first year. So that is the conditional probability. And conditional probability, there is a multiplicative. It is multiplicative in nature, and that's how we calculate the survival probability, which is a cumulative probability. Now, hazard is different. It is different. We should say that it is opposite of survival probability. But you see that in probability, the value of what is the range of value of probability? Yes, all of you please type in the chat box. What is the range of probability values? Yes, so Nitin is right. Sushri, Lavanya, Dr. Rath, yes, all of you are right. Anil, Rajat, okay, Rajat is also there. So it is between Nikhil, Ravi Shankar, Arif. So good. So all of you are right that it is from 0 to 1. But if you see the hazard ratio, it is always more than 1. It cannot be 0 to 1. So there is a difference. That's why I'm not saying that it is exactly opposite, because survival probability will always be between 0 to 1. But the hazard ratio, it can be less than 1 also. If it is protective, it can be more than 1 also. So it is a rate. That's why you will see there is a term is rate. And if you see the formula, in the denominator, there is a small delta t. We define it as delta t. That means at a very small time, because I said that it is an instantaneous rate. Because rates, that's just a very small fraction of time. What is the risk, or what is the risk that the event will happen? That is known as the hazard rate. So it is the opposite of survival. Not exactly opposite, but in somewhat understanding, you can say that if you know the survival, you can calculate the hazard, or vice versa, because they are related to each other with a mathematical formula. Here, now to understand it, what is a hazard rate? So while calculating risk, you will see that we have taken the entire time as a whole, but you may calculate the risk at each time point. So this is the example which you see that we have taken from the, in the last class, we have discussed about this, that maybe you can take as after knee arthroplasty, what is the probability that the person will be ambulatory. So this is for the male and this is for the female. So you can see that the females are ambulatory early and males became ambulatory in the later part. So you can again calculate hazard rate for each of these two groups, and you will see that it is less in female. That means female gender is protective for the hazard. Now again, it is the same. You can see here that this is the first week, and in the time period we have calculated the any outcome. So let's say it is a risk of death in the, there are two groups like experimental and control group. Something is popping over that. Can you see that? So risk of death, you can say that there are two groups, experimental group and the control group. So if I say that the number died during this time period is 3 in case of experimental group and 4 in case of a control group. So the risk of death will be like 3 by 100 and 4 by 100. And if you calculate the proportion of patient dying from experimental arm, so it will be 0.75. Similarly, if you go to the second week, Here also you can see that the 6 people died during this time point and 8 people died during this point, and this is the dropout. So again, you can see here, we are not considering all those because this hazard rate, this dropout is useful for the survival probability. Here we are calculating the proportion of patients dying in the experimental arm as compared to the control arm. So this is only to show you that proportional hazard assumption, that each time point, if you see these two ratio, you will see that it is nearly same, 0.75, 0.74 and 0.75, 71. So this hazard ratio is the time to event analysis. And here it is expressed as the hazard in the treatment arm. In the denominator, you take as a hazard in the control arm. And as we have talked, that this is an instantaneous event rate, and it is a probability that an individual at time t has an event at that time. In this case, you assume that the person was like till just before time t, he was free from that event. Now, how to interpret this hazard ratio? So like you calculate the relative risk or you calculate the odds ratio. Here you calculate in hazard ratio, it takes into account both the number of events and the timing of each event. So hazard ratio 0.5, what does it mean? So it means that at any particular time point, the half patients in the treatment group are experiencing an event as compared to the control group. If the hazard ratio is 1, then you say that the event rates are same in both the groups. And if the hazard ratio is 2, then we can say that at any particular time, twice as many patients in the treatment group are experiencing an event as compared to the control group. So this is in terms of a ratio. If you want to express it in percentage, you can also do that. This is just the formula. Like in linear regression, how do we express? This is y is the dependent variable. This b0 is a constant or intercept. And then beta 1, x1, beta 2, x2, beta 1 and beta 2 are the coefficients. And x1, x2, xn is the independent variable. Here, in case of how do we convert, what is the mathematical function of this hazard ratio? So here we take ht at time t, because I said to all of you that this ht, in this case, we take both the event and as well as the time. So it is the hazard rate, and it is expressed at ht is equal to h0. Instead of plus, there is a multiplication here, and this is the exponent. So exponent of beta 1 x1, beta 2 x2, beta 3 x3. So if you want to remove this exponent, you will have to take the log. So if you divide both the side of equation by a log, then it will be a log of HTH0 is equal to beta 1 x1, beta 2 x2 and beta 3 x3. So this is the function of the hazard ratio. So interpretation, if you want to express this as a percentage, then how do we do it? So it can be interpreted as 100. In the bracket, what you do, you deduct 1 from the hazard ratio. So if the hazard ratio is, let's say, less than 1, 0.76, then the value will be negative. So that means that much percentage decrease in the other group. Or this is done when you say that when the covariate increases by 1 unit. This is when there is a independent variable, is a continuous in nature. Just like the interpretation of odds ratio. And if it is a categorical variable, then what do you say? Then you say that much again increase or decrease as compared to the second group or the comparison group. So here you can see in this graph what you can see, there's a x-axis and there's a y-axis. In the x-axis, it is the years, like 1.5 years, 1 year. It is a study where they have seen like the risk of death is less in the atorvastatin group or placebo group. So in this case, you can see this dotted line, this is of the placebo group, and this solid line is the atorvastatin. And you will see that in case of a hazard, the curve is opposite as of the survival. Because in case of a survival, you see that the survival probability which we did in the beginning, that was going down with time. Because we read regarding the characteristics of survival curve. It starts from 1, where everyone is there, but with time it gradually comes down, and theoretically it will touch the 0. But till that time, we don't follow any study. That's why generally we leave the study in between. The curve of hazard ratio, it is opposite. Why? Because with the time, there is a risk of, or the person, not risk, the person is experiencing the event. So that in delta time t, there's an event rate, and with time that event rate is happening. So that's why the curve will be ascending. It is going up, you can see here. So here you will see, if you see the hazard ratio, what is the ratio? Ratio is 0.64. So the formula which we have given, like you have to deduct 1 from this. So what will be value? 0.64 minus 1. So the value will be negative, multiplied by 100. So 0.36 multiplied by 100 will be 36%. And it is 0.36. So we can say that the risk in atorvastatin group is 36% less, not risk. I'm sorry, I'm using the term risk. The hazard in the atorvastatin group is 36% less as compared to the placebo group. And this is at any given point of time. That's the proportional hazard assumption. Now, there is something known as the multiple collinearity between the independent variable. So ideally, you can check it by 2 or 3 ways. There is a value of standard error. So the desired value of standard error is between 0.001 to 5. And if you check it, you can get it. If the values lies outside this, then you can say that it is a multiple collinearity. But this output we don't get in JAMOVI. That's why in JAMOVI we check it through the correlation table. So I'll show you how to do that. So let's go to the, all of you can open your data sheet. I'll show you the table also before we go to the analysis. Table of the article per se. So this is the article. You can see that this was the title, Breastfeeding Education, Skin to Skin Contact and Other Determinants of Exclusive Breastfeeding. The data set which we have shared with you people, that is the data set which we have generated for this article, so that you can do the analysis, you can read the article, and then you will have a feel how this survival analysis is done and how this is interpreted. So I'll just show you the statistical part. So you can see the statistical analysis and sample size calculation. So now coming to the sample size, yes, one important issue which we did not discuss. So the consideration of sample size is exactly same that of a logistic regression. So can anyone type in the chat box, how do we roughly decide for the sample size calculation in case of a binomial logistic regression? Yes. 1:10, Bhumi is writing. Anyone else? So Bhumi is right, it is like in a range. We generally take 10 to 20. So what is 1 in this case? Bhumi, can you elaborate more on that? Independent variable. Okay, agree. So Bhumi is writing that per independent variable, or we say that yes, how many variables you can take for modeling? So let's say there are 10 variables. Will you take each 10 of them? No, there are ways to do that. First, you run the unadjusted hazard that you have seen, univariable. If the value of P, so that was another criteria. That is what variable to take. But again, if you have planned to take, let's say 5 variables, so then you have to, yes, Ravi Shankar is right, based on the proportion of outcome. So we say 1 per, like 10 per 1 variable, that is a 10 outcome. So you will say that 10 outcome you should expect for 1 independent variable. That is a minimum. Ideally, we say at least 20. So that's why there is a range from 10 to 20. But here they have used a statistical formula. If you see the article, using skin-to-skin contact as a main explanatory variable, we performed a sample calculation by using the following parameters. Considering the incidence rate of abandonment of exclusive breastfeeding of 2.8 event per 1,000 patient days. So they have calculated using the this incidence of 2.8 events per 1,000 patient days, and they have calculated like with the 204 patients. So that was the sample size they have used at, and the final sample size they have calculated as 363 diets with 302 exposed patients and 61 unexposed patients using the statistical power. Now coming to the, if you see the descriptive statistics, I'm reading out this statistical analysis. So descriptive statistics were performed using the percentage of categorical variable with median time. So this is the median survival time. For discrete variable, they have performed a log rank test for equality of survivor function to assess the differences in the duration of exclusive breastfeeding. We have seen this in the last time. And then they have estimated the crude and adjusted odds ratio per each explanatory variable. In that sense, they have built a multivariate. They have written multivariate. Ideally, it should be multivariable Cox proportional hazard model to evaluate the independent association between each explanatory variable and actual time in days to the, they have not used the term cessation of breastfeeding, rather they have used the abandonment of the exclusive breastfeeding. So now they have made a saturated model. So what is a saturated model? Saturated model, when they take all the variable which they think that is important, and then they have used a term like a parsimonious model. What is a parsimonious model? Parsimonious model is like the significant in the unadjusted hazard model, all those all those variables where the p-value was more than 0.2. So how to decide which variable to take? We discussed this in the logistic regression also, and the same rule applies here also. You are not very much rigid for this 0.05. Ideally, what we say, the variables which are significant in the univariable survival analysis, we take those variables into the multivariable. But here, we don't take that strict classification of 0.05, rather we take it up till 0.2. So all those variables where the p-value is 0.2, we may take those variable in our modeling. So that's why they're in what is a parsimonious model. So you can see that parsimonious model is a model where they have included all those final variables where the value of p was up till 0.2, and they have chosen a final model according to the level of significance from the likelihood test. Right. So this they have written, and then they have talked about the missing value. So since missing value was less than 1%, so that's, I'm not going into the, because there is another calculation. How do we tackle those missing value? And then you can see here that they have taken all these variables into account. Now coming to the table, if you see the table, I'll come to the table once again once we do the data analysis. So this is my JAMOVI sheet. So all of you, please open your JAMOVI. Have you, I'm just deleting all the analysis so that you may see it from the beginning. Yes. So all of you have downloaded the data sheet. Can you please write yes or no in the chat box? Have you downloaded it? And should I be telling you people from some basics of JAMOVI also, or I should directly go into the JAMOVI? So Dr. Khurshid is writing, okay. Yes, ma'am, basics I should be telling little bit, okay. So I'll be telling you a little bit of basics. So this is the JAMOVI interface. So what is the advantage of this JAMOVI? So there is a basic workshop also. We are conducting a basic workshop towards the end of this month. I guess the dates I'll tell you probably at the end of the workshop, and you people can join. It's a 3 days workshop on the basics of JAMOVI. But I'll be telling you here also. So you can see here that there are in the upper ribbon, you can see there is a variable, this is the data, this is analysis, and this is edit, and these are the other functions. So this is the variable. If you see, click this, these are the variables. So I'll show you what are the variables. This is the diode ID. What is a diode? I explained that diode is a twin pair of mother and the baby. So this is the diode ID. This is the gender of the baby. This is the marital status of the mother. If you double click this, you can see the name of the variable also. So I have just written, you can see, this is how you write the variables here. It is the measure type. You will see it is the nominal versus ordinal and continuous. So this is a nominal variable, male and female. I have given the code of male as 1 and female as 2. So normally you should have a data set in Excel. And then depending on the nature, you can either import it in JAMOVI, you can import it in SPSS. And this, the beauty of JAMOVI is it can import all sort of data, all file. I'll show you what all types it can import. Again, if you, there are this, these two arrows are there. If you go like this, you can see like this is the marital status, single mother as well as the married mothers. And then if you go like this, it will show you the other variables like education, higher and lower. Again, given code 1 and 2. This is the breastfeeding education session. Since it is continuous, so I have changed this to a continuous, and this is the sign of a continuous variable, because continuous variable is also known as the scale variable. That's why you will see there is an icon of scale here. So, and then if you go ahead, you will see that this is the milk production, whether what is a perception. So this was the variable, whether they have asked from the mother, how do they perceive, whether they have got very little milk or moderate milk or a high milk, because you know the breastfeeding also gets affected by the perception of mother. So this is an ordinal variable, or you can say it is a categorical variable, whether they have been asked regarding their perception. If you go ahead, you can see this is skin to skin contact. If there's a no skin to skin contact, so Dr. Ravi Shankar is asking, this is Excel or JAMOVI data. So this is a JAMOVI data which we have imported in the Excel sheet we have imported. We have shared all the 3 data sheet with you. Same data sheet in Excel, in JAMOVI, and in SPSS. So for those of you who have the SPSS in your, you can open either. But for those of you who don't have JAMOVI, first go to Google and download JAMOVI. So this, I'll show you that also. So you can download. So this is how you can see the variable. So I'll again go here, and you can see that this is the, you can go to the Google. You can type here JAMOVI. If you type JAMOVI, there's some it is showing that is not private. Again, I'll go with this advanced. Let me open some other. So you can write JAMOVI. Why it is not showing JAMOVI to me? No. It is that internet connection. It is showing it is not private. JAMOVI download. Probably it will. Are we connected through AIMS? Advanced. No, in advance also it is not showing. So maybe we are. Open incognito. I have to open it in incognito probably. Because our institute, they have like blocked, I guess, all these. That's why it is not showing. So what you can do, so that I'm just thinking why they have. So in incognito, you can type download JAMOVI. Here also they have blocked it probably. They have downloaded it. Okay, if they have downloaded. On cloud, yes, Dr. Pratish. It'll be allowed on cloud. Okay, Dr. Saxena is writing. I don't know, something has happened with our institute ID there. Never mind. Import data. So now I'll show you how to import data. So this if you click this will be like closed. This is the data. This is a icon. Okay. Yes. It is very simple. You can just type download and JAMOVI for Windows and PC, and please download the solid version, because the current version, there are some modifications. People are writing the codes. So for beginners, or even we also go for the solid version, because there it has been certain that all those functions are there. Now if you see this icon, can you see this? For those of you who are new, you can see this one, this, and click this icon, and then you can see there's icon known as open. So if you click open, it will ask you to browse the data, and then you can browse it here. You can show it a path from where you can download it, and then you can see it can have all data files. If you see, it can have a R file, Stata file, JASP file, Excel, CSV file, SPSS file, everything. So if you click on, then it will import. Since I have already imported, that's why I'm not showing you. In the JAMOVI also, you can see there's a data library. So if you don't have a data and you want to practice, so you can click this data library, and here you will find many library. The big five data set, the tooth growth, the bugs, the JAMOVI has given. So this is the library, but we are going for this PC. So that's why we don't need this. Now coming to the analysis. So analysis, we have seen in analysis, you click. We have also shown that how to install the module, because if you download the basic module of JAMOVI, it will not have these functions like the survival and all those. But for survival, what you do, can you see a plus sign here? So click this plus, and here you will see that there is a JAMOVI library. You go, and then you see you type the survival, and then you can no, that is not because, let me see. It is not because of survival. They are saying it's not valid. If you type survival, self-signed certificate. There's some problem with the net, I guess. Should we change to this other network? So if you see this, you can, it will come to all of you, survival module, and it will be in the form of this survival. Can you see this survival? So there are two modules, you have to download this death watch, and there is a module which is the clinicopath survival. So all of you, please download both these two, clinicopath survival and death watch. So I'll show you with this survival analysis. First, we'll see univariate. So if you see the univariate, I'll click this. And in this case, you can see what are the various boxes where we have to enter the variable. So this is the time elapsed. Time elapsed is we have seen this is the time to event data. So I'll shift this time to event here. Outcome is the this event. So if you click this event, you can see there are two, because now I'm not telling you about those sensor data, censorship and all. Why? Because we have discussed this in the last class. Censorship or the sensor data is a special type of data which you will find in the survival analysis, where there is a two type of censoring, like right censoring, left censoring, and sometimes we define something as intermediate censoring also. So right censoring is like those, how to define the censoring, that the observed survival time, whatever the survival time we have observed, that is not the true survival time. It is always less or more than the true survival time. So this actually it happens when either our study ended before and the person did not meet the event, like in case, or the person there's a loss to follow. So that is the right censoring. So censoring, that means we don't have the exact survival time. The observed survival time is not the true survival time, and it is generally less than the actual survival time. So here there are two, in the drop down menu you will see there are two options: continuation of exclusive breastfeeding and termination of exclusive breastfeeding. So which is my event here, continuation or termination? So that's why I said that definition of event is very important. In the last class, we discussed that you have to define what is the event. So event in my case was the termination of breastfeeding. Yes, Dr. Ravi Shankar is very much true, right? So I have clicked here as a termination of breastfeeding, exclusive breastfeeding. So this termination is my event, and then explanatory variable, let's say I'll take only one. Why? Because it is unadjusted. So it can have only one variable. So I'll take probably this gender of the baby just to show you. So this is the gender, and if you see, this is the summary table which you have to see. I'm not showing you the other output. So if you see, you have to focus on this. So what is the value of this hazard ratio? This is 0.82. Is it significant? It is 0.2. So now who will tell me? Should I take this in my final model or not? Although it is not significant. But first, let's understand the meaning of 0.82. Who will write it? Okay, Dr. Ravi Shankar is writing, can consider, very right. Now coming to the first part of the question, 0.82. How to interpret it? Taking that formula, protective. Dr. Vetrival is writing true. But if I want to write it in percentage, how will I write? I told you, hazard ratio minus 1. So 0.82 minus 1. So it is 18.18 multiplied by 100. But since it is negative, so less risk. So what I will write? 18% less risk of termination of exclusive breastfeeding in female babies as compared to male baby. Or you can write that female babies have a 0.82 hazard, this hazard rate less than as compared to the male baby. Or 82% of the female, they are having that particular event as compared to the male. So you can talk using all these three criteria. Interpretation. But again, many of you have written that since the unadjusted hazard is 0.2, so you can take that into the final, because we are not very rigid about that 0.05. Rather, we keep the cutoff. Yes, Dr. Mohammad Ansari is also right, 18. We keep till 0.2. Dr. Krishna, you are also right. Now, this way you can do it one by one. But the JAMOVI has got a beautiful feature. If you go to the multivariable, it gives you both the univariable as well as multivariable in the same table. So it is very easy for you, because in the same setting, you can keep on moving the variable in and out of the domain. So we'll just see how to do that. So I've just shown you for explanation. Otherwise, even if you use this, let me show you. Go to the survival and go to this multivariable survival analysis. So click on this multivariable survival analysis. And you see that they have also used multivariable. So the correct term is univariable and multivariable. It is not univariate and multivariate. Those terms we use for the dependent variable. If there are more than one independent variable, we use variable. So multivariable survival analysis. What is my, I will right now, I may take, since I consider that I have adequate sample size. So for just demonstration purpose, I'll take all the variables. So how I will do? I will click this to the time elapsed, this event to outcome. I have not checked the, first let me do the checking of the, what should I check? Assumptions. So assumptions, I said that proportional hazard assumption. In the JAMOVI, to check for proportional hazard assumption, normality, generally we don't check it here, and that I assume that you have done it, because in the descriptive statistics, you will do all those things, like checking the normality, mean, median. If you want to show the difference of some mean between the two groups, you can do. But this is purely, we are restricting ourselves to the survival. So I'll show you that can you see I have there is a function known as the RG editor. So using the commands in RG editor, you can check for the what you can say proportional hazard assumption. And there's a time dependent covariate also, that also you can check. But in the JAMOVI, to check for a proportional hazard assumption, you have to write commands, right? And I am not telling you for now those, because it will complicate the things. So maybe people are writing up in few months also, maybe you will have a command through which you can check, because we check it through log minus log curve. So that option is there in the SPSS. So that's why I'll have to show you SPSS also. And if you see, this is the same data set which I have imported in SPSS. So how to check for assumption? In SPSS, you can go. So Dr. Indranil is asking, how can I use this, my study on patient population coming to emergency? ER is emergency room, I guess. Can you specify the study? Yes, you can definitely use. If you have got a time to event data, then you can use this. So you go to this survival and you go to this Kaplan-Meier. You can go to the Cox regression. Here you can write it is the time to event. Here is the time. This is the event. Here you have to define event. So I'm giving code 1 to it. Continuous. In the covariate, you can add like few. This education and breastfeeding, this thing, and skin to skin contact. And then go to the categorical. Here you have to define all the categorical, like skin to skin and breastfeeding. Then continue. And here in the plots, you will see that there's a log minus log curve. So if you want to see it across the, let's say for the education. So I'll click this for separate line of education. And this you have to check for each variable separately. And then continue and press OK. So you will see that it will give you a curve. It is taking some time. So you see, this is the log minus log curve, LML curve we say. And you see that the hazard are same across the two levels of the education, like higher and lower. And this we did in the beginning of the session, where we have shown you that the ratio is same. That means if the two lines are nearly parallel and they are not crossing each other, you can say that the assumption of proportional hazard is there for this variable. So you will take all those variables where the proportional hazard assumption is there. But again, I said that till now, the JAMOVI doesn't have a command-based option for checking this proportional hazard. That's why you can use the SPSS for this. Otherwise, we'll make a short video, because till now we are also exploring. We tried to explore those written commands, but we could not do it. So we'll do that, and we'll update over our website how to check for the proportional hazard assumption in JAMOVI. But on SPSS, you can do that. But yes, that linearity, multiple linear, the other assumption was the multiple collinearity. That you can do over the JAMOVI. So here, how to check for that? So how many variables, if you see these variables, how many continuous variable can you identify, all of you? Please write the name of continuous variable. I just want to see in the chat box. Can I have a look at the chat box? Out of 42 factors does not satisfy, can we continue with analysis? What's the adjustment? 42 factors I did not get. Okay. Birth weight, gestational age. Okay. Lavanya has written the whole. Okay, good. Thank you, Dr. Bhumi Rath. You have identified it correctly. So if your independent variable has only G stat, G stat you are writing correctly. GG plot we use. Oh, G stat you are saying this. No, we don't use this. There's a GG plot which we use. So right now we will not tell you those things. Yes. So if there is only one variable which is continuous in nature, will you still go for this multiple collinearity? Nitin is writing how to install survival analysis feature. So that is by the plus module. Nitin, you can click on this plus. Right now, because of my institute network connection, it is not showing. But if you click the JAMOVI, oh yes, you can type survival here. Right now, it is there. If I type survival, you can see there are two modules of survival, this death watch and J survival. You, because it is installed in my computer, that's why it is writing installed and installed. But for all of you, it will write install. So you click on install and then it will be installed and it will show you here on the upper tab. Did you get it, Nitin? Okay, thank you. So you can now see that, so where, what I was discussing? Yes, I was discussing the multiple collinearity. So you said that if there is only one variable, independent variable, which is continuous in nature, then there's no need to test for multiple collinearity. Why? Because there is only one variable. But since in this case, there are more than one variable, like gestational age, birth weight, and this breastfeeding education, there are three. So how will I do that? I'll use a correlation matrix. So I'll go to this exploration, and in exploration, you will see there's a scatter plot. So click on this. Oh, sorry, not scatter plot. You go to this analysis and click for this regression. So this in regression, you will see that there is a correlation matrix. You can transfer these variables like gestational age, birth weight, these three. Because this time to event is the dependent one, that's why I'm not taking. And then see the value of correlation coefficient. Now you have to tell me, seeing the value of correlation coefficient, which of the two variables are highly correlated to each other. Can you all see that output? Birth weight and gestation age. Agree. All of you are right. Dr. Bhargav, Dr. Anil, Lavanna, Vetrival, Rath, agree. So you can see it is the 0.9 here. And if it is so much correlated, having a correlation coefficient of 0.9, there's no point taking both the variables. So you'll take only one, right? Because the other two, it is very less. You can see here, it is, okay, this is also very significant. Oh no, this is p-value. Otherwise, this is showing 0. This is also 0.03. So these two are having less correlation. So now I'll use only one of these two variables, gestation age and birth weight. I'll use birth weight. So I'll go to this again, survival. If you double click this here, again it will come. So you can see that in JAMOVI, in the same interface, you can have a input and you can have an output. Whereas the other data package, you will see that analysis package, both the interface is different. Output is in the different tab and input is in the different tab. So that's why this is the beauty. And in multivariable, you will see that it has got two big boxes. So you can enter many variables here. So for now, I'm entering all. So this time to event, I will shift here. This is the event. I'll shift here in the outcome. My outcome is the termination of breastfeeding. I'll shift the explanatory variable in this. In this, you can see this icon. So this is the ordinal variable and nominal variable. So ordinal and nominal, I'll shift here. So gender, marital status, education. This breastfeeding session, this comes here as a scale variable. I'll shift this to here. Milk production again to this. Skin to skin contact here. Breastfeeding within 1 hour, this much. Gestation age and birth weight, since these two are highly correlated, I'll use only birth weight. And then you can see the output. So if you see the output, you will see that it gives you both the univariable and multivariable odds ratio in the same set. Now it is easy for you to delete the variable from here. So you will see the gender has got a p-value of how much? 0.2. So I will include that in my final model. Yes. Marital status is 0.02. I'll include this also. Education also. This also. Milk production. But this again, it has got a varied this thing. Skin to skin. If you see the other p-value. So here you will see that all the p-values are less. So I'm not deleting anyone. Now, if you see the difference. So this is your multivariable. This is 0.83. So you will see that gender, even after having all other variable, the hazard ratio is same. Gender is not to include. Why don't want to include gender? Dr. Anil, gender cannot be included because P is 0.2. But I said now that you have got this flexibility that you take all those variables where the p-value is up till 0.2. We are not that much rigid. But if you want to keep your criteria that you will take only those variables who are significant, that is up to you. But generally, you will see that with the adjustment, now many a times the variable which are like 0.2, that becomes significant. So that's why we say that you should include. But again, it is up to the investigator. If you think that no, you will get only those variables where it is value is 0.05, then you can go ahead. You can like choose not to keep the variable here in this case. So you will see here that it is 0.83. We'll see that education, it has now you see this. This is the beauty of this adjusted one. Initially, in 1-to-1, it was significant, this education. But in adjusted, you will see that it has become not significant. The p-value is 0.6. Similarly, this milk production also, you will see that initially it was not significant. Later it became insignificant. In skin-to-skin contact also, you will see that initially it was significant. But in final model, it was not significant. And if I go down, you will see that breastfeeding within 1 hour. Yes, it is significant. Initially, it was highly significant, but later but again, it is significant. So if you see the variable, like one of you, Dr. Dodoju Anusha has written like gender, marital status, skin to skin, and breastfeeding within 1 hour. That is the significant variable. If you go down and if you see like birth weight also, birth weight is not significant. So see, initially the birth weight was significant, but in the adjusted model, the birth weight was not, the birth weight was not significant. And here it gives you the value of the R square also, or the final model. And this concordance, can you see there is something written as concordance? Yes, can anyone tell me what is this concordance? R square, you all know. What is the meaning of R square? Means the value of this is, this R square is 23%. What is this concordance? You can remember, like with the logistic regression, you have that, you plot that AUC, area under the curve for logistic, isn't it? What is the sensitivity? What is the specificity of the cutoff which you have taken? Similarly, the model which you have given here, the concordance or the C value or the C index we call, it is 0.6. So if it is 0.6 and more than that, that is acceptable, but it should not be less than that. So that's the value of concordance here. And then I'll show you the actual paper, which how they have written. Because I told you that we will wait to see the result. If you see this is the initial descriptive. See, this is their table. So you can see they have also given like all the factors, the explanatory variable. In the second column, they have given the crude odds ratio, and then they have given the adjusted odds ratio. And can you see there are two terms, saturated model and the parsimonious model. So saturated model is when they took all the variables. And in the bottom, they have written, if you see this, there was found collinearity in the model between early to early skin contact, joint accommodation, timely ligation, umbilical cord breastfeeding within 1 hour. So those variables, they have taken that there was a collinearity. That's why they have not taken those variables in the final model. And then you can see here that like up till, they have also taken up till 0.2. So in the saturated model is when they took all the variables. So this is the p-value of the saturated model. So you can see in the univariable, it is 0.69. This is 0.02. So here you can say that p-value is 0.85. So they have not taken it in the final model. So these were the variables which they took, and they have removed all those variables, and you can see the odds, the hazard rate. And now we know how to interpret the hazard rate. So this is the table. You can directly, what you can do, you can copy paste this. You can just right click this, copy this, open a Microsoft Word, and you can click and you can go down. I'll show you, we have again pasted the same table here, but I'll show you how to paste that. You can come here, you can Control V, and you can see that this gets pasted. And then you can modify it a little bit more. It is again like a Microsoft Word. So you can shift all this, and here also it will give you the bottom, that footnote also. And you can write the interpretation. So we have tried writing the interpretation here, depending on what we have discussed, univariable and multivariable. And you can say that which were the variables which was, got included in your final model. So that's how you can perform the logistic, this Cox regression, proportional Cox regression hazard, multivariable. So I think time is up. And all of you who are interested, when are we flashing that? What are the dates for that JAMOVI basic?
28, 29, 38.
Okay, so 28, 29, 30th December.
29, 30th.
Okay, so last week of this month only, 29 and 30th, we are taking the basic of JAMOVI. So those of you who want to learn like basic one, you can enroll on that particular, it's a workshop. So you will have to like join, and then we arrange a breakout room sessions where you have to practice showing your screen like the way you are doing it now, just an extension of this. Otherwise, there are videos available. Yes, on mail. Mail it is, I think, can we do that? We'll share it to Clarnet, and then, because the Clarnet has got the email ID of these people.
Just
No?
Made in India पे जाके देखना ना, वहाँ सब course सब कुछ
Okay, so you can visit the site meritindia.org. I'll just show the flash the slide, and all the data set that is available there.
और data set PPT everything.
PPT, data set, recordings. So even if you don't want to enroll for a workshop because you want to learn it at your own pace, then you can, we have got the basic of course also for JAMOVI. It's free for everyone. So you can join and you can listen it, and you can like learn accordingly. And all the data set that is available on the website. PPT, everything is there. It is free. You can just visit and download it. Because I think Clarnet has got the access of all those emails. So it may not be possible for us to mail you people, but you can download from the website. Okay then, thank you so much. See you next year. Okay, we are ending it. And thanks to the Clarnet for this, for this media partner and your support. So our Clarnet, over to Mona Lisa.
Yes,
Are you
ma'am.
there?
Yes, ma'am. Yes, ma'am. So thank you so much for extending us the opportunity to host the session today. And thank you, Pragya ma'am, for your kind words. So with all your permission, we are concluding the session over here and really looking forward to hosting you again. Thank you so much, ma'am. Thank you, everyone.